Hello. In our previous lectures, we have defined the traveling salesman problem. We developed a mathematical programming formulation for it, and we learned a branch and bound algorithm to solve the TSP. But because of the size and complexity of the problem, solving the TSP, especially when there are large number of cities, using those branch and bound algorithm or exact algorithms takes a lot of computational time. If you need a solution in a short amount of time, then you need to develop a different solution technique. So in this course, we will learn about heuristic algorithms, and we will see two examples of such heuristics that can be applied for traveling salesman problem. Basically, we will learn a construction heuristic, which is named as the nearest neighborhood algorithm, and we will learn an improvement algorithm, which is named as the subtour reversal heuristic, so that we can easily find the solution for TSP. But be careful, heuristic algorithms provide good feasible solutions, but they do not guarantee optimality. Okay, so we will learn basically what are construction and improvement heuristics, what are their properties, very basically, and we will learn the main steps of nearest neighborhood and subtour reversal heuristics, and we will make some examples. So let's get started. Heuristics are solution methods for optimization problems, but they are not exact solution algorithms. So basically, we divide the solution algorithms into two as being exact solution algorithms. Okay, so when a solution algorithm is exact, it means that it guarantees optimality. For example, the simplex algorithm for linear programming is an exact algorithm. So it finds the optimal solution every time. Okay, so branch and bound algorithm for integer programming. It guarantees optimality if you go till to the end, if you do not stop with a time limit or something else. Cutting plane algorithms. Cutting plane algorithm. Again for IP. This is also an exact algorithm. But on the other hand, we have, for example, a Hungarian algorithm for the assignment problem. This is also an exact algorithm. It guarantees optimality. Okay, so for example, this transportation simplex method. Transportation simplex. It finds the optimal solution. Okay, Prim's algorithm. For minimum spanning tree problems, Prim's algorithm provides the exact optimum solution. For shortest path problems, Zigtra's algorithm for shortest path. Okay, so these algorithms are exact algorithms. They guarantee the optimality. But on the other hand, there are some algorithms which solve optimization problems, which provide feasible solutions to optimization problems, and they provide good solutions. Okay, in quotation marks, they provide good, but they do not guarantee optimality. And how do we know that these algorithms provide good solutions? Because they have an idea behind. They try to make good steps. They try to make good decisions, but usually they are myopic. They cannot see the future. But just looking at the current situation, they try to do their best. Because of this, they are named as good, providing good solutions, but they don't guarantee optimality. Okay, so what you need to know about heuristics is heuristic algorithms do not guarantee optimality, but be careful. Be very careful with this statement. This doesn't mean that heuristics never provide optimal solutions. Heuristics can provide optimal solution. But the thing is, you may not know, you do not know if that solution is optimal or not. But you will not know. You will not know that solution is optimal. That solution is optimal. Okay, you only have a solution. This is the solution provided by an algorithm, but you don't know if it is the optimal solution or not, because they cannot give you the guarantee. They can find the optimal solution, or they may provide you a worse solution. Maybe there's a better solution than the optimal one, and you will not know this as well. Okay, so these kind of algorithms are heuristics. Then why do we need heuristics? Because we explained for the TSP problem, the number of feasible solutions is huge. There are a lot of feasible solutions that you need to consider, you need to evaluate to find the optimal solution. Even with the intelligent methods like this branch and bound algorithm that we have seen, still you will not be able to find the optimal solution in a reasonable amount of time. But you need that solution in a short time. So what do we do? In order to obtain a good, feasible and usable solution, we use such heuristic algorithms. So for this TSP, in fact, the heuristic algorithm is not just a single algorithm. There are many different variations of these algorithms. The two important variations of heuristic algorithms are construction heuristics and improvement heuristics. Again, when I say construction heuristic, in fact, for TSP, you can write a lot of construction heuristics. Heuristic is not just a single algorithm. It is the name of a class of algorithms. Okay? So you may have a lot of construction type heuristics for the TSP, and you may have a lot of improvement type heuristics for the TSP as well. And what is the basic difference between construction and improvement heuristics? We will see. Basically, in construction heuristics, you start from scratch, you don't have an initial solution, and by following the steps of the algorithm, you come up with a feasible and good feasible solution. On the other hand, in improvement heuristics, you already know a feasible solution, you have a feasible solution, you try to improve its value by trying different alternatives. So in this lecture, we are going to see one construction heuristic, which is named as the nearest neighborhood heuristic, and we will see one improvement heuristic, which is named as the subtour reversal heuristic. Okay? So we will just see these two algorithms, but as I said, there are many different algorithms, and the number of algorithms is limited by your imagination. So you yourself can develop your own algorithm to solve this problem as well. And in order to solve a problem with a heuristic algorithm, you don't need to formulate, you don't need to develop the mathematical programming formulation. You can just start from the definition of the problem and develop a heuristic algorithm. Okay? So if you like, you can combine these two algorithms with each other, and then you end up with a new problem. So you start with the nearest neighborhood, you come up with a solution, and then you use that solution inside this subtour reversal heuristic and try to improve its value, and it is a new heuristic. Okay? So what you need to know about heuristic algorithms is this. They do not guarantee optimality. They are quick and easy methods. And when we talk about heuristics, always remember that we are talking about computer algorithms. These methods are implemented in computers using programming languages like Java or C++. Okay, and we solve the problems using such algorithms, and everyone can develop their own heuristic algorithm. But what is important for a heuristic is it should be quick, it should find the solution in a short amount of time, and the final solution, the resulting solution, should be high quality, should be good, a good solution. As I mentioned, in construction heuristics, in constructive type heuristics, you start from scratch and step by step you go to a feasible solution. But of course, at each step, while taking a step, you consider the objective function value. Therefore, at the end, you find a good feasible solution. You try to find a good feasible solution. In improvement heuristics, on the other hand, you start from an initial solution. Okay, this initial solution can come from a construction heuristic, and then starting from this solution, you move to a neighboring solution, and you compare this neighboring solution with the previous one, and you try to maintain the feasibility of the solution and try to improve the objective function value. So in this example, we are given 7 cities, and we are given the distances between each pair of these 7 cities. To reach from 1 to 2, 18, you can say kilometers or meters. From 1 to 3, it's 17. Okay, so there is a well-known algorithm, so-called the nearest neighborhood algorithm. It's very logical algorithm. Whenever you define this problem to someone and ask for how to solve it, people always come up with a similar algorithm. Okay, so how this algorithm works, let's see the pseudocode of this algorithm. It says that first randomly select a city and set it as the current city. So one of these 7 cities we are going to select, and we will set it as the current city. Then there is a loop here. You see, repeat until there are no unvisited cities. So it means that we are going to label the cities as visited and unvisited, and we will continue the loop until there are no unvisited cities. Okay, so what we will do, we will find the unvisited city that has the shortest distance with the current one. Okay, if equality, if there are 2 cities, 2 unvisited cities with the same shortest distance, then it says that select the city with the smallest index. Okay, sometimes in such algorithms, they give you the rule what happens under equality. Okay, if you are checking some condition and if there is an equality in that condition, what to do? In some heuristics, they give you such a rule. In some heuristics, they do not. If a statement is not made, then if there is an equality, you can do whatever alternative you like. You can select one of them randomly and continue with that. Okay? But here we have a rule, we need to follow this rule. And in the second step here, to I step, set this city as the current city and label it as visited, and then return back to this step 2 and continue until there are no unvisited cities. So let's solve this problem using this algorithm, very simple algorithm. We will start with one of the cities randomly. And let's assume that we are starting with city 4, okay, randomly. Then what we have? We are currently in city 4, so let me put a label over here so that we can understand we are dealing with 4. Okay, then it says that find the unvisited city that has the shortest distance. So unvisited cities are 1, 2, 3, 5, 6, 7. And I will look at this row over here. And inside this row, I will find the minimum Of course, the minimum one is this 0, but it corresponds to the same. So I shall not consider this column. Okay. Among the others, the minimum possible one is this one. Okay, there is no equality. It means that I am going to set this city 3 as the current city. So I'm going to write here current. Okay. Current city is 3, and we are moving from city 4 to city 3. Okay, now we finished this 2-point-second case, and we will return back. There are still unvisited cities, so we just visited 3 and 4. We are currently at 3. Okay, so let me put an arrow here. So we are currently here. And it says that find the minimum unvisited city. Okay, so we shall look at now this row. And in this row, the minimum unvisited one is this one, which means that from 3 we will move to 5. And our current becomes 5 now. Okay. So let me make these adjustments. So we are currently in 5. Okay. So there are still unvisited cities 1, 2, 6, 7. I will find one of them. Okay, the minimum shortest distance with 5. So I have to look at this current cities row, and I see that we have this city 1 as the shortest distance. So now we are going from 5 to 1. The current city becomes 1. Okay, and we will find the shortest distance from 1 to other unvisited cities. So if you look at this one, and this one, we see that 2 has the minimum. So from 1 we are going to 2. So 2 becomes our current, and here I need to write 2 as the current. And from 2, I will look at the unvisited ones, which are this and this, and I see that 6 is the unvisited one, so 6 becomes the current one. Sorry. Okay. So current is the 6, and since there is only one city remaining, I will move to 7. Okay. So this is how this algorithm works, but the question is, what is the objective function value corresponding to this solution? Let me write all these in this way. 4, 3, 6, 7. What is the objective function value corresponding to this solution? How shall we find it? So we will find it from this matrix. Okay. Basically, we will follow this route. From 4, we are going to 3. So the distance here is 4 units. From 3, we are going to 5. So the distance is 7. 5 to 1, the distance is 9. 1 to 2, the distance is 18. 2 to 6, distance is 23. And 6 to 7, the distance is 13. Sometimes students make mistake at this point. This is a tour, which means that from this last city you need to return back to 4. So sometimes they stop at this point, but sometimes in order to represent that we are returning back to the initial city, they write the initial city to the end as well. Or sometimes you don't write it, but basically you show it like this. So I have written it to the end. and the distance from 7 to 4 is 43. And the total objective function value, if you add up these, you will find 111. Okay, so this is the so-called nearest neighborhood algorithm. Let's consider another example, another TSP instance, and let's solve this problem again using the nearest neighborhood heuristic. So the distance matrix is given in this table, and for this nearest neighborhood, we can start from any of the 5 cities. In fact, if you like, you can develop your own method or rule to select the starting point. And each starting city may lead to a different tour. Okay, so if you start from 1, you may end up with one tour, but if you start from city 2, you may end up with a different tour. Okay, so if you like, you can try different versions. Start from 1 and find a tour, then start from 2 and find another tour, and then combine these two, compare these two, and select the best one. So let's assume that in this example we are starting from city 3, which is this one. Okay, from this city 3 we need to look at all the distances. Okay, and we see that the shortest distance is to 2. So we go from city 3 to city 2. Then we are at city 2. We already visited city 3, so it means that you don't need to look at this column anymore. We are currently here, and you will check this number over here. Of course, this is infinity, this number and this number, and the shortest one is this. So which means that, so you are going from 2 to 4. Okay, so the next one is 4. Then, since we visited city 4, and also since we also visited city 2, you don't need to check that one, sorry. And we are currently at city 4. Okay, we need to check this one and this one. The shortest one is this. So it means that the next city to visit is 1. And then since we visited city 1, from here, we are currently at city 1, the final one is to go to city 5 because it's the only remaining one. And the final tour is this one. And you can easily find the total length of the tour by just checking the distances, by just adding the distances in this final tour, which means that we are going from 3 to 2, so this distance, plus 2 to 4, which is this distance, and 4 to 1, which is this, and 1 to 5, this distance, and finally, don't forget, you need to return back to your initial city, which means that you are going from 5 to 3. So when you add up these, you will find the total distance of this solution. So the total distance, when you add up those, is 735. And as we mentioned previously, the quality of the heuristic depends on the starting node. Okay, so if we started from node 1, city 1 in this example, we would end up with this tour, and the total length would be this much. And when you compare these two, this one is better than this one. But how do you know before solving it? You don't know, you cannot know. But what you can do is you can try. So you can just solve the problem by starting from each of these cities and then compare them with each other. Then what you gain and what you lose. If you, for example, have 5 cities, if you just select one city and solve it randomly, you solve the problem only one time. But if you try to start from each one of these cities and then solve using the nearest neighborhood, it means that you solve the same thing 5 times. So the required solution time for the second alternative is 5 times the first one. And if there are, for example, 50 cities, then it makes 50 times the first one. Okay, the trade-off here is you try to improve your solution value, but you are losing from the solution time. If you really need a solution in very short amount of time, just start from a random city and solve it. But if you need really a good solution and you have enough time, then try different cities, try from each one of them, solve it again and again, and compare them with each other and select the best one. Now let's consider another heuristic, which is called reversal heuristic, or sometimes called subtour reversal heuristic. This is an improvement type heuristic. Okay. So you start from an initial feasible tour. We start from a feasible tour, and in this heuristic we try to improve this initial solution by making changes in the solution. And how are these changes made? As I said, you may define different type of improvement heuristics. You may modify the initial solution in different ways. In reversal heuristic, we modify it in this way. Okay, what do? Let's assume that we are given a tour. We reverse the order of cities. First, we reverse them. We reverse the order of consecutive 2 cities. So, for example, if the TSP tour, initial tour is this one, let's say 1, 5, 2, 4, 3, and back to 1. So we first try these 2 city subtours, which means that we reverse the position of 5 and 2, for example, and we obtain 1, 2, 5, 4, 3, 1. You see, these two are different solutions. From this one we obtain this solution, but of course we don't know if this solution is better than the other one or not. Then you need to calculate its objective function value and compare it with the other one. But of course this is just a change on the initial one, and we don't know if it is better or not, but there are other alternative changes. For example, we may change the order of 2 and 4, 4 and 3. Okay, so consecutive 2 cities. But the thing is, in this subtour reversal, if you change the order of 3 and 1, you see it will not produce a feasible tour, or you need to be careful in order to produce a feasible tour, and that's why it's not considered. Okay, so we just switch the order of consecutive cities other than the first one in the sequence. Okay, so of course we can make these changes for consecutive 2 cities, but we can also make the changes for consecutive 3 cities. For example, in this one, we can reverse the order of all these 3 cities, and we start from 1, then go to 4. The last one in this consecutive becomes the first one. 4, then 2, then 5. So instead of going in this order, we go in the reverse order. Okay, but only for these 3 consecutive ones, and all other remain the same. And of course we can do this in a different for different cities, and instead of using 5, 2, and 4, we could also change the order of these cities. So we may obtain 1, 5, then we will follow in this order, 3, 4, and 2 in the reverse order, and then 1. And again, we don't know, of course, if this is a better one or not. So we need to calculate its objective function value and compare with the initial one. And finally, we can also make a change of 4 consecutive cities other than the first one, and instead of going in this order, we can go in reverse order and say that, okay, 1, 3, 4, 2, 5, and 1. But you need to be careful with this last one. Why? Because you see, this is a tour, which means that we start from 1, then go to 5. Let me sketch it here. So this is 1, then go to 5, and then go to 2, and then from here to 4, then to 3, then to 1. Okay. So in this first one, we are moving in this order. But in the second one, we are going in this order. Okay. If the TSP is symmetric, meaning that going from 1 to 5 is the distance for going from 1 to 5 is equal to going from 5 to 1, then these two solutions are in fact identical. But if it is not symmetric, if it is asymmetric, then this is different. So therefore, we claim that if the TSP is symmetric, you don't need to perform this final one, and you can only continue until subtours of n-2 for symmetric case. Okay, for symmetric case, you go until n-2 cities for a TSP with n cities. N is the total number of cities. Okay, but if it is asymmetric, so you can continue, you can make all the changes up to n-1 consecutive cities. Okay, as I said, this is an improvement heuristic. And what do? Basically, we first generate all possible new solutions by reversing the order of 2 consecutive cities. Then we make, on the same initial solution, we make the changes with 3 consecutive cities. Then with 4, 5, up to n-2 for symmetric case and n-1 for the asymmetric case, and calculate the objective function value of each one of these and select the best alternative. Let's consider the same example that we solved with the nearest neighborhood algorithm, so for which the distance matrix is given in this table. And this is, we are going to apply the reversal heuristic or the subtour reversal heuristic. And this is an improvement algorithm, which means that you need to start with an initial solution. And this initial solution for this example is given to us. Okay, so how did we find it? Someone gave it to us, or for TSP, you just randomly order the cities and you obtain an initial solution. And we can calculate its corresponding objective function value using this table. So 1 to 4, the total distance for going from 1 to 4 is 150. And then you add up all those distances, 4 to 3, 3 to 5, and etc. And you obtain this objective function value. Then let's apply this subtour reversal heuristic. How do? We start with this heuristic. Okay, this is our starting solution, and first we apply changes for consecutive 2 cities, which means that we first change the positions of this, the order of this 4 and 3. So when we change their order, we obtain this new solution with this objective function value. Again, we can calculate it using this table. And then we change the order of 3 and 5 in this solution, and we obtain this new solution with this objective function value. Okay, what do? We need to calculate, or we need to identify each such new solution by applying all possible changes, and then we calculate their objective function values. And when we do all of them, we will compare the best one with the initial one, and we will select which one will be our solution. Okay, so here, what do we have? We calculated, let's say, this one, and then what do? We change the positions of 5 and 2 to obtain this new schedule, this new sequence, and we have this objective function value. Okay, so these are all the possible changes and all possible solutions that we can obtain by changing the positions of two consecutive cities. But then we can change the positions of three consecutive cities. Which are they? So we can, for example, change the order, reverse the order of these three consecutive ones, and instead of 4, 3, 5, we obtain 5, 3, 4, like in this schedule. And when you find its total distance, we see that it's infinity, because basically you see that this diagonal is infinity, but as well as some of the moves are also restricted in here. And as you see, going from 4 to 2 has a distance of infinity in here. That's why the total distance is infinite. Okay, so on the other hand, we can make another change with three cities by reversing the order of these, and we obtain this new solution. But again, we are going from 4 to 2 in this new solution, and again the total distance is infinite. And since and we can try, since this matrix is not symmetric, you see it is not symmetric because this and this is different and these two are different, so it's not symmetric. It means that we can try reversing n-1, which is 5 minus 1, 4 of the consecutive cities, and we reverse their order and we obtain this schedule, this new sequence, and then we calculate its objective function value. Now these are all possible new solutions that we can obtain from this starting solution. Okay, so which one shall we select? Of course, we should select the one with the minimum total distance, which is this one. Okay, so this is the solution that we obtain from this starting solution. The final solution depends on the initial solution. If you start from a different initial solution, you may end up with a different final solution. It can be better, it can be worse. We don't know which one will be better, but still the objective here is you have an initial feasible solution, and with this algorithm we improved its value. Okay, so improvement algorithms work in this way. The general idea is this, and this is how improvement is done with reversal heuristic. As I said, there are other methods to find. For example, one method is called insertion. Okay, instead of subtour reversal, you can use insertion. And what do we have in insertion? For example, if you start from here, this solution, then in insertion, basically, you take one of the cities from its current position and you place it to somewhere else in the sequence. For example, you can place it here and then you obtain a new solution. Basically, when you place it here, it is the same solution that you obtain here. But also you can take it from here and place it here, so you obtain 1, 3, 5, 4, 2, and 1. And then you can take it from here and insert it to here, and you obtain this solution 1, 3, 5, 2, 4, and 1. See? So what do? We take a city from its current position and insert it to somewhere else in the sequence. Okay. Similarly, we can take this 3 and insert it to here, and we can take 5 and insert it to here. You see, this is different than the subtour reversal, and it provides different solutions. And still, we don't know if it is better or not. You need to compare the objective function values of the new solutions with the initial solution and select the best one. So for this example, with subtour reversal heuristic, we obtain this final solution with this objective function value. Let me repeat some of the notes about the subtour reversal heuristic. So this reversal heuristic does not include the starting city, as I said. It is not included because when we reverse, for example, 1 and 4, you see you are going from 4 to 1, then to 3, then to 5, then to 2, then to 1, then to 4, then to 1. So in fact, it is not a tour. Okay, 1 appears twice here, not at the beginning and at the end. Therefore, we do not include the starting city in this reversal. The final solution that you obtain is a function of the initial feasible tour that you start the algorithm. And for this, you can try it by yourself. You can repeat the same algorithm, but start with a different initial solution. Do it by yourself. It's a good exercise. Instead of starting with the given solution, you just select another solution, random solution, and apply the subtour reversal heuristic by hand. Calculate the objective function value for each of the new solutions that you obtain by reversing 2 cities, 3 cities, and 4 cities, and compare your final solution with the initial solution and determine the best one, and then compare this final solution with the solution that we obtained here, okay, with starting with the given solution. And they may be the same, but also they may be different from each other because the final solution depends on the initial one. For this purpose, for example, start from this tour. The initial length of this tour is 750, and use the subtour reversal heuristic, okay, and find the improved tour. Of course, there may not be any improvement. Maybe this is the best solution. This initial one can be the best one, so that after those trials, you will see that none of the new solutions are better than the previous one. Of course, you will keep the previous one as your best solution. If there's an improvement, okay, you will select that one as your final solution. Okay, so compare this solution with the previous one. Okay. Another exercise for you. Consider this TSP example. Solve this TSP using the nearest neighborhood heuristic. Remember that algorithm. Start from a city, and at each step from that city, move to an unvisited city with the shortest distance to the current one, and find your final solution. And then in the second step, okay, apply this subtour reversal heuristic to the solution that you obtained in the first step and try to improve its value. Okay, so this is another exercise for you.